Assalamu alaikum. My name is Hamzal Imran and I'm a grad student at School of Electrical Engineering and Computer Sciences, NUST, Islamabad Campus. The paper which I'm going to present today is based on the initial work which we have conducted at our department. So let's move towards the slides. So the title of our paper is HARDenseNet, a one-dimensional DenseNet inspired convolution neural network for human activity recognition with inertial sensors. This work is conducted by me and my colleague Mrs. Kiran and Osama Latif. As you know that artificial intelligence, machine learning and deep learning are becoming pervasive these days. And human activity recognition is an active area of research, which has many applications that include sports, child monitoring, social networking, entertainment, healthcare, and etc. Traditionally, human activity recognition was done with the help of computer vision techniques, which has many limitations that include high operational cost, productivity, portability, privacy, occlusion, etc. The use of inertial sensor has improved all these limitations. The use of deep learning neural networks with inertial sensors can be extensively found in literature these days. So in our paper, we have proposed an architecture which is inspired by DenseNet. DenseNet was proposed in 2017 for image classification task. The speciality of this architecture is that on every layer we have the feature map of all the previous layers present there. So this helps in doing better classification, because on the end when we are doing classification we have the all sized features available for us. Moving towards our contribution, so in this paper we have three major contributions. That includes that we have presented a novel one-dimensional convolution neural network which is inspired by DenseNet. The second is we have evaluated its performance on three different human activity recognition datasets. Lastly, we have done a pretty comprehensive literature review, when in this paper we have reported 14 articles. Starting with the first dataset, that's called smartphone dataset. In this dataset, the dataset was collected with the help of Samsung Galaxy S2 smartphone. 30 volunteers were involved. There are 6 different classification classes available, which are walking downstairs, walking upstairs, walking, sitting, standing, and laying. We have divided this dataset into 3 different parts that are training, testing, and validation. 70% for training data, 15% for testing, and 15% for cross-validation. We have used the raw sensor values for our deep learning model. Moving towards the second dataset, which is by Wisdom Lab, Wireless Sensor Data Mining Activity Lab. The dataset is called Activity Prediction Dataset. It also has 6 classes that include standing, sitting, downstairs, upstairs, jogging, and walking. And we have also divided this dataset into 3 sets. That's 70% for training, 15% testing, 15% cross-validation. It has around 10 million entries in it. The next dataset is also from Wisdom. It's called Wisdom Acti Tracker Prediction Dataset. This also has 6 classes, but different than the other datasets. That's stairs, lying down, standing, jogging, sitting, and walking. It has around about 3 million entries in it. You may have observed that all the 3 datasets are unbalanced. So therefore, which makes accuracy a less accurate measure. Therefore, we have also reported F1 measure, recall, and precision for individual classes as well. So this is the overall architecture which we have proposed. Let me explain it in the form of chunks. So we have 3 such modules. These modules have 10 one-dimensional kernels with a size of 3. Activation function which was used was ReLU, and then we have a dropout of 0.5. The C block here is called concatenation. So after every module we are concatenating the feature map from the previous layers. Lastly, we have 2 dense layers which have 100 neurons in them, and activation function was ReLU again. This overall picture depicts the entire architecture, which has 3 such modules, and then we have 2 layers, a fully connected one, and then we are doing the prediction using the softmax classifier. Moving towards the results, so this is the confusion matrix for the first dataset, smartphone dataset, we achieved 91.61% accuracy. You may see that our architecture is basically suffering in classifying these two classes, sitting and standing. Other classes are being classified relatively better. And the same thing can be observed in this performance report as well. This report is showing you the recall, precision, and F1 measure for all the classes. Again, the value of recall is least for sitting class, which can be observed from the confusion matrix as well. The second dataset results, we achieved 94.65% accuracy, and the performance is much better than the previous dataset. The same thing is depicted in this performance report as well. Lastly, for the third dataset, which is ACTI tracker dataset, we achieved 77.18% accuracy, and this dataset is struggling in classifying between laying down class and sitting. The same thing can be observed in performance report as well. You can see the details in the paper. Recall, precision, and F1 shows the entire performance of the architecture. Moving towards the training of the architecture. So for training, we have experimented with different optimizers, Adam, RMS Probe, Adagrad, etc. Adam seems to perform the best. The epoch size which we set was 100, and batch size was set to 120 for all the three different datasets. Here is this table shows the software stack which we have used to deploy the model. TensorFlow and Keras was used for the deep learning work. Then Seaborn was used for plotting different matrices. Pandas and NumPy was used for data manipulation. Entire experimentation was done on Google Colab with GPU set as an runtime environment. Moving towards the future direction. So basically, as mentioned in the beginning of the presentation, this work is a part of initial study which we conducted at our department. The future direction and work on which we are currently working at is this, that our target is to efficiently detect offering of namaz. So the application is that the mobile phone present inside the pocket of the person who is offering the namaz is capable of detecting that he or she is offering it, and it's going to silence the phone during the offering of the prayers. After that, the phone would be set to unsilent mode if the person wants. Concluding my presentation, human activity recognition is an active area of research. Considering its many applications that from different domains that include sports, healthcare, child monitoring, patient monitoring, etc., we have presented a novel architecture which is inspired by DenseNet. It has one-dimensional convolution layers. We have reported not just accuracy, which is a common measure in literature these days. We have also reported recall, precision, and F1 measure considering the unbalanced nature of the datasets used. The accuracies achieved for the three datasets were 91.61%, 94.65%, and 77.18% respectively for smartphone wisdom ACTI prediction and ACTI tracker dataset. Thank you very much for attending my presentation.